So good afternoon, everyone. Sorry. I'm Christopher Yin. I'm an MLOps engineer at Recycley, and my talk today is on garbage in, garbage out, applying AI to waste management. So I'm going to give a brief summary of what I'm going through today. I'm going to start first off on who we are as Recycley, what we're doing, and what we're trying to achieve, and then the benefits of working with different waste data, and then moving on to the ML challenges that we face when working with waste data, and the different approaches we take to solving the problems, and finally moving on to post-deployment monitoring that we implement. So who are we? Recycley is bringing advanced machine learning and computer vision and robotics to the global waste management industry. We're working with recycling. So our clients are recycling facilities. They are plants that, or we call them MRFs, and they process a lot of recycling waste. And we're trying to use AI to help them improve their quality control they have on the waste, provide them with better data and analytics, as well as helping them capture higher value of waste flows. So why are we trying to solve this problem? We're trying to solve this problem because globally in 2019, more than 460 million tons of waste was produced. And of that, only 9% of the plastic was recycled, and more than 50% of the waste goes to landfill. And so how do we aim to solve this problem? We aim to solve this problem by overall lowering the cost of recycling. So currently how the recycling industry works is waste would get collected and be sent to a plant, and they would hire people to manually sort out any high-value waste they can find. And because it's very expensive to hire people and sort it out manually, they only want to sort the waste that can generate a lot of value, or else it doesn't make sense for the recycling facility to sort every single type of waste because they won't be able to generate any profit. So with our vision and robotics system, we would be able to sort at a lower cost because we're able to sort 24 hours a day. And overall, this would lead to a reduced cost, which gives the recycling centers a higher incentive to sort out more types of waste. So maybe lower value waste that they didn't use to sort out, they would be able to generate more value, and this would lead to an increased amount of recycling and less waste that ends up in landfill. So here's a little demo of our robotics and vision system. So on one side is the robot, which uses a pneumatic system to pick up all the different types of waste and put it in the relevant bins. And the other side is the vision system that we implement with ML, with an ML model, and it does the classification, object detection, as well as give an overall confidence of the different type of classes. So what's the type of data we work with? We work with RGB video at HD resolution. And this is a decision we made because it is cheap and it's simple to implement. So we want our overall system to be, the cost to be low so that more people can implement it. And compared to what is being used in the recycling industry right now, they use near-infrared cameras, which could cost up to 50,000 pounds per unit, while our unit costs maybe less than 10% of that. And it also means that it's simpler for us to be able to install our vision system at the client site. Let's move on to the benefits of working with waste data. So the first benefit is that we don't really have to deal with the privacy issues that most vision applications has to deal with. So most vision applications, you're working with facial recognition or any application that if you record someone, you'll have to, the data will be really sensitive. While our data is because it's household waste, no one really cares about the waste that they throw away. And so there isn't really a privacy issue there. The movement of the videos that we capture, the movement of the waste is also really simple. They normally come straight down the belt most of the time. And the final benefit is that because we're working with businesses in terms of our clients are recycling facilities, they're able to collaborate with us to iterate through the different type of models. They also allow us to collect data on their site prior to deployment so that we're able to get as accurate of a data as we can to when the model goes live. So let's move on to the challenges we face when working with waste data. The first challenge is that it comes in a lot of different types of forms. So here we have examples of HDPE milk bottles. They could be crushed, they could be soiled, because waste doesn't really get treated well, and like most of the time it gets rained on, there's mud, there's dirt. Some people also leave milk-filled bottles and it goes into the waste recycling facility. And sometimes, a lot of times, it's also ripped as well. So you get like a top half, middle half, a bottom half of a bottle. The same applies to PET bottles. It could be inflated, crushed. A lot of times people like to put the packaging, so they take the little wrapping outside of a PET bottle and they shove it inside of the bottle. I think a lot of us do that. And this just overall complicates the task of recognizing the type of waste, because the ML models that we develop has to be able to recognize all the different classes. So this is only one example of HDPE milk bottles, and it just comes in a lot of different forms. The next challenge is working with clients from a lot of different countries, which leads to a large variety of waste. So an example here is one of the Heart ice cream brand by Unilever. And there's more than 20 different names that they brand their ice cream depending on which country you live in. And this again poses a big challenge, because it means that if we have a model that has learned a type of shape or packaging for one type of material, we would struggle to do the same in a different country, because even though it's the same product, it gets branded differently. It might be in a different colored container or a different size container. Another example is, you can see from the glass bottle here. Prior to seeing this glass bottle, we did a lot of work on training a model that could work on a glass line. But then we discovered that there are places where they do PET, so plastic glass bottles here. And this is done by the manufacturer to reduce the overall cost for transportation, but more importantly, it's used in big sporting events so that people can't use the wine bottles as a weapon, or it accidentally gets dropped and injures someone. So that's another challenge, in that even when you think you understand, okay, wine bottles are always made of glass, then there'll be manufacturers that create them where it's made of PET or some other type of plastic, and we have to be able to understand it and sort it correctly. The next challenge is the environmental factors that we have to deal with. So we work with a lot of different recycling facilities, and all of them have their own ideal method they've come up with to transporting the waste and making it easier for the people to sort them. So these waste facilities aren't the cleanest places in the world. They're really dusty and they're dirty, and they cause a lot of noise in the video that we work with. The lighting condition could also change a lot. So we could put our vision system next to somewhere where there's a lot of natural light. And if we calibrated it when there wasn't any sunlight and there is sunlight, then it causes the images to be overblown, and we lose a lot of the detail, as well as the fact that the reflectiveness of the objects change a lot. There's also a huge variation in conveyor belt designs and widths, as you can see here. So the middle image, it's a very narrow belt, but it's very deep to stop all the waste from falling out on the side. And then for the other two images, you can see there are chevrons on the belt. This is to stop the waste from falling backwards when it's going up an incline. So this poses challenges in that the background constantly changes, and it means that the model would struggle to be able to differentiate whether it's a new background or it's a new object. Finally, the waste doesn't really get treated well, and it gets stored outdoors a lot, which means that it'll get rained on, especially in Scotland. And it means that, as you can see from the two images here, it means that overall, the top image shows the belt when it's dry, and the bottom is when it's wet. The belt color changes significantly. It also means that the objects that we're dealing with, the reflectiveness also changes a lot. The final challenge we have is to do with seasonal data drift caused by seasonality. So I have two examples here. The first is when we worked to collect trade and val data sets from a site in Dublin, and it was an aluminium line, and we happened to be there maybe 1 or 2 days after St. Patrick's Day. And we ended up, our model was really good at recognizing Guinness cans, because there was a lot of Guinness cans in the data set. And this might only be useful maybe a few days in a year, but once the waste went back to the normal type of waste that we get, we found that our model didn't perform as well, because it was really good at Guinness cans, but not really good at everything else that we had to use. Another example is during Christmas celebrations, there is a lot more Terry's chocolate orange packaging that we have to deal with. And we found that our model, because it hasn't really seen this type of packaging, it would confuse it with orange juice cartons, which matters a lot when it comes to the recycling aspect, because the packaging looks really similar, but Terry's chocolate orange is treated as gray board, while an orange juice carton is treated as Tetra Pak, which contains a gray board, but a lot of other factors such as like aluminum film to be able to protect the product inside. And so we want it to be sorted in a different category. So a quick review of the challenges that we face. The first is a high amount of variation in the waste that we get. We're working in a constantly changing environment, and there are a lot of seasonality causing data drift we get in the waste that we're working with. So now let's move on to the solutions we have. So there are two solutions. The first is a general approach, which is where you take a big base model, so an RCNN model, and you feed it a lot of data. So this is talking about millions and millions of images. And normally this data set would be of a low quality because there's a lot of images, and you wouldn't be able to spend the time to clean up and make sure all the data is at a high quality. And this would take days to train because this is a very GPU intensive process. It would mean that it would take days to always create a model. And of course, you would find mistakes in the data set. You want to add more data to the data set. And it would, again, if you want to keep going through the cycle, it would take days to ever get a new model. So the approach that we took, or we found to be the most efficient, time efficient, is to take the general approach and use that as a pre-trained model. So we take advantage of transfer learning. And then we're able to go to the client site and collect data that is as closely representative to what we get in a live setting. And when we call that a fine-tuned data. And then we take the pre-trained model, and then we train it in addition on this fine-tuned data, which only takes hours to train because this data set is only maybe tens of thousands of images. We're also able to quickly iterate. So as I talk about the data drift issues or maybe objects that the model's never seen, we're able to add that into the fine-tuned data set. And we're also able to correct the mistakes that we find in the labeled data and be able to iterate a lot quicker. This only takes hours to train instead of days. So training a model is only half the solution to making a good getting a good solution. The other half is to do effective data labeling. So we've kind of come up with a pipeline to be able to ensure that we get the highest quality data in the shortest amount of time so that we can feed it into our models. We first start up with non-expert annotators. So they're really fast at annotating all the different waste objects, but they make a significant amount of mistakes. So as you can see here, the top image, we have something that the labeler has labeled as gray board. And if you look at first sight, you'll think, yeah, that looks like a piece of gray board. But if you look at it in more detail, it's actually an Oatly milk carton, which would actually be classified as Tetra Pak. So this would be a mistake that we'll have to spot in order to ensure that our model is performing well. So we then move on to an experienced annotator. So someone who has local knowledge of household products, and they would be able to make the type of corrections you see here and ensure that our data set is at the highest quality. But even then, there are still issues that we have. So you can see from the two white plastic cups here, one's actually made out of polystyrene, while the other one is made out of polypropylene. So that's treated differently as well in the recycling industry. And so to deal with these issues, we will request for samples from the clients. So this is a very expensive and time-consuming stage because we'll have to ask them to send us examples of waste data they have, and we'll have to understand, build an understanding of what type of waste they have, what are the issues that our model is dealing with that's incorrect, and be able to make the changes to our data set to reflect it. And even with all these steps, there'll be times when there are anomalies that end up on the belt. So example here is a frying pan that ended up on our aluminum belt. Another example is a little kitten that, when the belt stopped, decided it was a good time to take a sleep underneath our vision system because of the warmth provided by the LEDs. All right, so the final section is about post-deployment monitoring. So it's only half the battle to be able to deploy the model that is doing well, but you have to constantly monitor the performance of the model to ensure that it's still performing to the client's needs. And we do this by monitoring the overall model confidence. So if the model confidence drops, then we know that there's something that needs to be done. We also detect changes in the distribution between the different classes. So if we look at it, it could be that the model is performing well and that there is data drift and our model is still able to recognize all the different classes, which leads to the distribution changing. But it could also be, most of the time, it's because of the fact that our model is no longer performing well in one of the classes that we're recognizing, which leads to an overall change in the distribution. If these solutions don't work or we're not able to spot how the model is performing, again, a very expensive and time-consuming step would be to evaluate the pick purity of the robot. So the robot would pick all the objects and put it into a bin, and we would go to the client site, and we would take out the bin, look at all the, so let's say HDPE bottles it's supposed to pick. We would count all the HDPE bottles that it's picked, as well as all the anomalies, so we can evaluate the overall performance. If we're unable to get access to the client site, then we would count the detections. So we take a look at the recording of the video and would manually count the number of detections the model is making and whether it's making any mistakes or not. So in summary, we have been able to solve a lot of the issues when working with waste data. And we've deployed 17 robot and vision systems to clients in 6 different countries. And we make around 100,000 picks of waste objects every day. But this is only the tip of the iceberg. So we're currently applying this to household waste, but we want to be able to, or we see an application to use this technology to be applied to industrial and electronic waste as well. Thank you.